Hello and welcome to another video. Today's video is actually a continuation of my previous video, which was machine learning, aka artificial intelligence, 3 types of learning. In that video actually we discussed about the 3 types of learning in machine learning field or any kind of AI field, which was supervised, unsupervised and reinforcement learning. But when I was actually explaining those 3 types of learning, I've used a number of time a word called model. Right, so what we are going to do today is actually going to discuss about that model. What are those models? How do we use them? What is the mathematical progressions, or you can say mathematical precisions to actually calculate all the things to get a final output? How are we going to do that? So we are going to discuss that today in today's episode. So we call them nothing but neural networks. So before understanding the artificial neural network, let's just understand the natural neural network, which is inside our brain. So, a brain consists of 100 billion neurons, near about 100 billion neurons, if I've checked in Wikipedia. Yeah, it's about 100 billion neurons. So, each neuron actually looks like something like this. It has a cell body. Let me just draw this up. Okay, so it goes with the random orders. So okay, you have something called some kind of spider-like thing called over here, and this is called as a cell body. The cell body. So this cell body, everybody knows. If you have ever attended a biological class of 8, 9, 10 till your medical classes, of course. If you're a medical student watching this video, you have, of course, have an idea that what the heck this neuron is, right? Even the students of 8 and 9. These are dendrites, of course, dendrites. These are dendrites. Then there are axon terminals. So, what do we have here? We have a really, really important and also really beautiful gift from nature, of course, a neuron, which actually help us to do everything in our day-to-day life. Sitting, standing, sleeping, eating, shitting, everything, including everything, just everything, even from single process of our body, is also communicated to the brain using this neuron. Actually, the brain is itself a really big house of neuron, where it does not have any kind of processors, but the neuron says ones and zeros, communicating in ones and zeros to actually cut off the powers and continue the power to actually perform some kind of action. So that's what the neuron works like. So what we are going to do in neural network, actually going to replicate this neuron into a software. Let's just understand how does this work. These are dendrites. Some kind of input goes into this neuron through these dendrites, and this cell body right over here, this little guy's cell body, takes actually integrate those input and then pass those input to an axon and throw that to the axon terminal, which will be an output. The output, this will be input. That's how a normal cell body, or you can say longest cell of the brain called neuron, works. Okay, that's it. So let's just try and think how does an artificial neural network will work. Okay, so let me just clean this up. Let's just try this. Let's just do this, and this will be gone away. Okay, so let's try this. 1, 2, and 3. Okay, that worked. Okay, perfect. So we have both clean. So if you have checked my previous video, which is in my channel, If you're new to my channel, please go and check that playlist called Artificial Intelligence, aka Machine Learning. Okay, so opposite the title is. Okay, it's the opposite. Machine Learning, aka Artificial Intelligence. I've made a diagram, a reference diagram of some kind of thing like two. Oh, sorry. It's just okay. Let's make it two. Three of them. Then we have 1 and 2. Each of them is connecting with some things, and some things. Right? So what we are going to do is now do this thing. How does this model work? We have, for example, we have a data set, but we need something. We need some kind of medium to actually analyze those data sets, to give us a final output, to do something, some kind of prediction, to generate something, right? So we need something. That's what we are going to talk in today's episode about this model. So we are done with the natural neural network, natural neuron. So we'll be talking about artificial neural network. Artificial neural network. Okay, so that's gonna be pretty easy. So let me do that magic again. So okay, that worked again. So what do we have here? Is just a neuron. If you have a neuron, we have some sets of input and one output. Now we usually denote this input and output like we denote these inputs like x index 0, then x index 1. This is actually the processing unit where all the input flows to this and some kind of mathematical process happens inside the neuron. So we'll denote that as this sigma sign, and this output is being sent out to some kind of threshold. Yeah, some kind of threshold. This looks something like this. I will explain you each and everything. Just let me give you a basic idea of the neural network. A perceptron is shot. Then, after passing some kind of a certain threshold, it will give me an output denoted as like y1. So for now, not for now, every time we have 3 steps to do. We have 1 to get the sum. Second, activation function. Okay, function. Quite long to write this. Oh my gosh. Third is the error rate. Okay. So we are going to cover step by step. First step sum, then second is activation function, then third is error. Okay, so yeah. Okay, finally we are in here. So what this perceptron does is it has some kind of input, right? For example, if I give an input of 0 to x, let's take it as 1, because 0 will be quite complicated for you all guys, because you're new. So let's take it as 1, right? So the 1 will flow directly to the sigma and this processing unit. Now, it actually there's no logic that will actually connect this node, input node, to a hidden node. What this processing unit is called is hidden layer. What this input layer is called yeah, I just told that. Input node is called as input layer, and this is called as output layer. So we need something to actually connect this input node with the output node, right? Because whenever we talk about neural network, for example, I'm going to say I want to build a 2-layered neural network. So at that point, we are not talking about these 3 layers. We are just talking about the hidden and the output layer, because input layer does not matters at that cases. We don't count input layer while building some kind of neural networks. We just give him the input, do some multiplication, some kind of addition, and some output is generated. So at that point, we don't need some kind of connections over here, but we need some kind of connections over here. So what do we call them as? What do we call them is weights. Yeah, weights. Now you must be thinking, weights? Come on, I'm not overweighted, I'm not underweighted. What the heck is weights? Now, weights are nothing but synapse. Now you must know about synapse. Synapse is actually a gap between the two neurons in a biological term in neuroscience, where the input flows and it jumps up to the next neuron with the connection of the synapse. There will be a small gap between the two neurons like this, and the input signal, actually the signal will jump onto the next neuron using the synapse. And synaptic fluid is actually involved in that procedure too. So yeah, that's why we need this. And for x1, we of course, that's so there's weight 0 for input x index 0. So for x index 1, we need weight 1. So easy, right? Yeah, it's recording. I thought it's not. Wait, sorry. Okay, so input flows in. The input flows in, get multiplied by the weights, and it's just passed on over here. Now, but it will not directly flow to the Y output, but something will be added to it. We call them as biases. I will talk about the formula. Wait a second. Even I need to talk about the biases. So, wait. So, let's just write the formula what we are talking about right now. So, x index 0 times weight index 0 plus x index 1 times weight index 1. So what this does is nothing but to, as you can see, the x index 1 is actually multiplied by the weight index 0, and then it is added to the x index 1 and the weight index 1. What was that? It's about a freaking thing. Okay, yeah. Sorry for the distraction. Let's concentrate. Yeah. So then it depends upon the input layers. How many input layers do you have? And it gets all multiplied by the weights and added to all the input layers and all. You cannot do just that. Will not be ideal while doing in programming, that we are declaring each and every variable of x index 1, x index 0, 1, 2, 3, 4, 5, 6, 7. What if we have input layers till 100? You cannot just do it like a stupid person. Just keep declaring all the variables of till x 100, index 100, and multiply those all with the x w index 0, 1, 2, 3, 4 till 100. That will be so stupid, and also will be time consuming, or it will need more computing power. So to actually reduce this down is what we need, this kind of sigma, sum of all of them, right? Sigma weight, x 1 or 0, whatever, then we'll be weight 1. Not only this, now I was talking about biases, right? So biases are nothing but a node which will actually fit the data into the model. For example, if I got input of 0, okay, what if I got an input of 0? So 0 times any number will give me 0, right? And that will not be ideal. That will be always negative or false. How computer chips actually recognize those information in ones and zeros, same goes over here. It actually just traces on and off using that activation function, which I will explain you before. Which I will explain you, not before, after. What I'm saying, I will explain you. Wait. Okay, so 0 times anything will give me a 0. That will not be ideal. So we need something to add with all of these. If the answer is 0, if the input is 0, we need something to get add to better fit, or you can say shift the data, shift the input layer, input input to fit the data into the model. That's why we use biases. Okay, that's why we use biases. That's it. So we are done with the sum. So we are done with the procedure of sum, right? What is a sum? Is this formula right over here. Sigma, whatever number of input and weights are, will be added to a biases. That's it. And we are done with the sum. Let's now talk about the really essential and very important part of any kind of neural network, which is an activation function. Remember this. This is a really important term and also really important keyword in the terms of neural networks. What an activation function does is, for example, if I have a computer chip, so it needs some kind of zeros, ones, and zeros and ones, right? To actually fire the computer chip to run some kind of program or do some kind of certain task. For example, I have a light. Okay, yeah, light will be a good example. If you have ever worked in Arduino projects like that, you must know, or you can. Okay, I have a really good explanation for this. If you've ever seen a computer, inside the computer, there is a motherboard. Of course, you have some kind of RAM and all those slots in that. You have some kind of LEDs which turns on and off and on and off. Whenever you click a mouse, it turns on and off. There are some kind of systems in that. What it does is, when you click up a mouse, it sends a input of 1, and when you don't click a mouse, it sends an input of 0, which will tell the computer that the mouse has been clicked, and 0 will tell you that the mouse is not clicked. The clicking over here, same goes for neural networks. When input flows, so you have the answer, for example 1, or something, I don't know, this is ideal, not so ideal, but something will actually pass through this activation function, and or you can say a certain threshold, which we call as an activation function, will say that do this neuron needs to trigger or not, yes or no. In binary language, 1 or 0. If the input is 1, the output is 1, so of course it's gonna fire the neuron, because the binary language, the 1 means yes, so activation function will take that as yes, and will just fire the neuron up to do some kind of certain task. But if the answer is 0, of course it's not going to allow the neuron to work on some kind of specific task it has been told to, if the input or the answer is 0. So yeah, that was all about the activation function. So activation function, let's do it mathematically. The same thing applies over here. Let me just make some space. We have a sigma x1 times y1 and bracket plus the biases. Now something will be actually multiplied by this thing. What we call this as activation function, which will be 1 or 0. The activation function's values remains only the 1, because the answer will always come into 1s or 0s. So activation function multiplied by 1. If this is 1, the answer is 1. So 1 by 1, if there's 1 into 1, it will always give me 1. So that means yes. 1 into 1 will give me yes. But 1 times 0 will give me no. That's how the activation function works. Now we know how does the input works with the weights, with the hidden layer, then goes to a certain threshold called activation function, give me the output. Is that it? Is that it? No, not at all. We are still remaining with the third step called error. Now it's not that kind of error when you play Assassin's Creed or Dying Light, you're setting up the game and you get an error called Steam _ API.64.dll is missing from your computer. That's not the error I'm talking about right now. Error is something what you guess, what you desire to have, and your model predicts some kind of guess. You minus those values, and you get the answer. What we call that as error. Now, for example, I'm going to take for example, let's take it about a plane. Let's take about a car. A car will be a good example. For example, I want to go from this waypoint to this one. I have a car over here. So I want my car to actually go over here, right, to point B. But what my car gets to go is over here. So by tweaking some kind of tweaking the model or the programming side of neural network, I can steer the car in some kind of particular direction or particular degree to move towards B, point B. So that will be my, for example, the difference between over here and here is, let's say 90 degree. It's 90. Okay, let me just clean this up a bit. I'll just love my okay, I just love my hands to do on this. Okay, this came off. I really don't want this. Yeah, sorry for the distractions. Yeah, so let's take this as it has a 90 degree, right? 90 degree is the desired value. Let's call that as dv. 90 degree is the desired value. Well, the guess value is 45 degree. Right? That's my guess value. GV. Okay. So we have that. So we have a guess value and a 90 degree desired value. Now let me show you that how does this error works. Let me just clean up the board. Let's just do that magic again. If it works, again, please work. Okay, that worked. So we are at the car, right? So I have a car. Let me just draw that again. Car, we have point A, point B. My desired value is to go from here to here, which is the length over here will be 90 degree. I want my car to move at 90 degree to go to the point B. Okay, so my desired value is 90 degree. The steering angle will be 90 degree, and what my car guessed is 45 degree, which will be a half of the 90 degree, 45. So I want some kind of tweaking inside the model to actually steer the steering wheel to move more 45 degrees. So 90 degree minus 45 degree will of course give me